All right, ladies and gentlemen, welcome to Emerging Technology special lecture from Professor Samban Ring from PXL, good friend, university of ours at Lapin UAS. We have had a lot of cooperation with them and ongoing stuff, and Professor Van Rijn is going to give us a presentation about LLM security. And without further ado, Sam, the floor is yours.
All right, thank you very much, Kenneth. All right, so let's dive into this topic immediately. We don't have a lot of time, and this is quite a big topic, actually. So let's just go. I have a few disclaimers. I learned that from a colleague of mine. Always handy to put some disclaimers. So this presentation is in the context of the LLASER project. The LLASER project is a Flemish government-funded project around large language model security. It only started recently, like at the end of last year. So we are still building up our knowledge and expertise in this area. And some of the information in this presentation is actually very, very fresh. It's actually from last week because I attended quite an intense workshop around this topic, around the topic of red teaming LLM applications. So that means this presentation is a bit untested in the wild. So we'll see how it goes. And we have limited time, as mentioned, so I will go over the NLP background stuff a bit more rapidly because, as far as I know, a lot of you already have some background in that. So I will just briefly go over it again just to have the context fresh in memory. So that's a bit the idea. So the LLASER project is, we are working together with KU Leuven Discinet, who does more the fundamental research around this topic. And our job as PXL Smart ICT is to get this information and spread it widely, right? To spread it to companies, to the industry, to other students. That's a bit our job. So that's what we are going to be doing here. So let's start a bit with some AI security and privacy in general to basically create the context, because I'm not sure how much you guys are aware of the extra security threats that AI poses, but I'll just briefly go over it to set the scene. So when you put an AI model or an AI application in deployment, it can be a tool, hopefully, a functioning part of the system, something that helps, something that enables whatever you want to do with AI. But it also becomes a target, right? The AI component is a vulnerable part of the system, and it introduces extra attack vectors. And additionally, and I took this metaphor from a colleague of mine, but it can also be a fool which unintentionally harms the system. So it serves multiple purposes, but it's also something that can be under attack and that can unintentionally harm the system, as mentioned. So let's first look at the target part. So what if an attacker knows that a system or a product is based on AI? Then that means the AI model can become the target. Yeah, so because involving AI in your application means increasing the threat landscape. So more attacks are actually possible because AI models have specific vulnerabilities that can be exploited by specific attackers. So that means the threat landscape of AI looks a bit like this. You have, first of all, model manipulation, where if you have a existing trained model deployed somewhere, it's possible to corrupt the model itself. There is also output manipulation, where you manipulate the model's response to specific requests. You basically devise a certain request which will kind of corrupt the output you get from the model. And also information leakage, where you are able to extract information from a model that you actually shouldn't be able to. Yeah, and this happens with systems with AI at their core, but also systems that interact with or depend in some way on AI. Yeah, so that's a bit the threat landscape. You have two times or two instances where this can happen, and that's at training time and at inference time, where something can happen or the AI model can be attacked in some way. So if you take a sort of ML DevOps pipeline of AI models, this is just an abstraction. I'll be using a lot of these schematics, but hopefully they are clear enough. So you have training time, where of course you have the whole data acquisition and processing part, and you have the model design, the model training. And then at inference time, you put a trained model into production and you interact with it as a user. So during the model training, you can poison the model somehow or introduce backdoors into the model in some kind of way. An attacker can do this, not you, but an attacker. So that means basically that you modify training data or you modify model weights if you're using like a neural network using certain adversarial techniques, right? So you can, the goals can be like backdooring the model, introducing biases, degrading the performance, causing misclassifications, manipulating outputs. And it's quite difficult to do this because you have to know quite a lot about the training process and the data that's being used, but it can lead to highly destructive outcomes, right? Because you are compromising the model's integrity and performance. And there's a lot of ways to do this. I will not go into a lot of detail on the ways to do this. It's just to give you a bit of an overview of the threat landscape. So if we look at LLMs specifically for the poisoning part, there was a paper that came out. In the meantime, it's been like last year or 2 years ago, I think, that showed how cheap and easy it is to poison the data collection for LLMs. Right, so it introduced a few data poisoning attacks that were actually very practical and easy to poison popular data sets that LLMs use as training data, right? So, and it only cost $60 to basically implement this attack. So, very interesting paper, definitely worth looking into if you want to know more about this. So that's at training time. You also have potential problems at inference time, where you have the output manipulation, stealing the model or stealing at least a similar functionality to the model, membership inference, where you extract what kind of data the model has been trained with, model inversion. There's many different things. I will just take a few examples. And it's always easier to use some like image classifiers because that makes it a bit more visual and a bit more clear what could possibly go wrong. So, for example, if you have a classifier somewhere that tries to classify traffic signs, you have it trained, it works well, it sees a stop sign, great, it classifies that as a stop sign. But what you can do is influence, or you can corrupt this the data you sent to the model like this. You carefully optimize a certain kind of noise vector and you add it to the input image, and then suddenly it completely changes how the model reacts to it. And you can do this by, it's basically also kind of a machine learning process where you try to figure out what kind of noise would actually make the classifier flip classes. Yeah, that's the idea. So AI, when you've trained a model properly, it can be robust to noise and random changes. But when you are an attacker who wants to really strategically manipulate the output of the model, then you can by finding a carefully optimized noise vector that corrupts the output. The other thing I mentioned was information leakage, where you have, for example, membership inference. And this is, I think, the CIFAR 10 dataset, one of the famous image processing datasets. And researchers showed that you could actually reconstruct the original input data based on just interacting with the model. by interacting with the model and trying to basically get out of this model what the neurons had kind of memorized. Because when you don't mitigate this, powerful AI systems, in this case, a image classification system, actually memorizes some of the training data in a sense. Also applied to LLMs. For example, you probably heard about the New York Times having a lawsuit against OpenAI. I think this was like a year and a half ago. Actually, not sure how that turned out, that lawsuit eventually, but they claimed that OpenAI used the New York Times articles to train their model illegally without adhering to copyright laws and stuff like this. And actually, there was they were able to extract exact parts of New York Times articles from ChatGPT. Well, I think this was GPT-4 at least. And they were able to extract, again, training data that was used for GPT-4. And by doing this, they saw directly that New York Times articles did appear in the training data of GPT-4. So all that to say that robust AI, and with robust we mean secure and safe AI, it's an open problem. Yeah, so certified and provable robustness is kind of out of reach at this point. There's a lot of research in this area, but it's an unsolved problem. So the only way to mitigate it is by empirical testing and certain defenses, and we'll get into that at a later stage as well. So we call AI robust if it can maintain its goals under unexpected changes and under attacks. So now that's when AI or an AI system is a target, but it can also be a fool, like we mentioned, where it unintentionally harms the system. Because you don't even really need an attacker to fail you. Sometimes it's just about misplaced reliance. And this can be because of bias in the training data. And this is just a model that doesn't operate the way you want it to. So it can be because of bias in training data. It can be because of changes in the data or the environment. It can be because of privacy violations, semantic gaps like shortcuts. I could go into detail about this, but you've probably heard about some instances where this happens, where, for example, you create a classifier that differentiates between a wolf and a husky, and the way it does this is by just focusing on the background instead of focusing actually on the thing that we want the model to focus on. So this is an example of shortcuts. And it can also generate faulty or harmful content. We know this from LLMs. They hallucinate this kind of stuff. So there are many things that can actually make the AI system fail, and it doesn't even have to be like a deliberate attack, right? So AI failures must be anticipated. So you might be wondering, when we have these two cases where AI in deployment can be a target or fool, do LLMs solve these problems? And I'll leave that question hanging for a little bit, because you probably already know the answer to this. The answer is no, they do not, and they actually introduce even more problems. So let's go into a little bit of an NLP recap, just to get everybody on the same page. And I've used some slides that I use in my classes on NLP for this, and I'll like as mentioned, I will go over these quite quickly. So if we take just as a use case, we want a spam classifier, right? So we give it text messages, and we try to classify if it's spam or not. The label is 0 non-spam, 1 spam. So the problem is text messages have variable length. Text messages are not numeric because AI models need numeric input, right? So what to do? Well, basically, in order to numericalize this text, we tokenize and we pad this text. So you probably know a bit about tokenization and vectorization. Tokenization is basically just means that you put all the available words in a sort of dictionary, and then you index into this dictionary, and those indices are your tokens in this case. Yeah, so basically you split your text into tokens and you make every sequence equally long, in this instance at least. So we have a tokenized input where you have here these indices into your vocabulary list, and then zeros to pad the sequences to make all of them equally long. So for example, you have a bunch of input text of 512 tokens. Yeah, then you send them through a embedding layer where you vectorize the input, and that means you create, these embeddings, which are semantic representations of words that actually carry some meaning. That's the next step. And for our intents and purposes, we just, the input text, we just flatten it into one summarized input representation. We throw it through a standard neural network like this. Here you have a few layers. And then eventually you classify it as spam or not spam. This is a very simplified architecture for to use for a NLP problem. So you are familiar with all of these concepts. If I'm saying stuff that you're like, I have no idea what you're talking about, then please speak up or raise your hand or something like this, because I will go over this quite fast. Is it okay? Yes. All right. So let's move on to language models. So this is just a spam classifier, which is a more simplistic NLP problem. But so a language model is something that predicts the next word in a sequence. All right. So it's really about text generation. So the classic example, the students open there, and then you want to basically be able to predict the most likely next word. That could be books, laptops, exams, or minds in this instance. So the idea is really to, when you have been given a sequence of words, to compute the probability distribution of the next word. So this is all the previous words, and this is then the next word, and you try to figure out what's the most likely one. And the handy thing about a language model is it's kind of model that understands the given language. So it understands relationships between the words and the tokens, and it's kind of and you can use it as the basis for other classification problems, encoding or decoding, machine translation, summarization. It can be used for many different tasks. And I say that it understands the given language. There are some caveats to that, of course, but at least it understands how language works. So, and you find this everywhere nowadays, of course, these language models, but also these are some more older examples. Like, for example, language models have been used in Google since already like over a decade, probably. But we associate it most with like all the hip chatbots of today. So if you take that standard NLP architecture of before, where you have a tokenized input, you add an embedding layer, and then you flatten the input to predict the next word, it's kind of insufficient, right? Because the summary of the input, it's not really, it's insufficient for the next word generation because it doesn't take into account the context. It doesn't take into account, the sequence of the words that happened before. So you need something different, right? And that's where recurrent neural networks came from, where we basically made a sort of looping neural network, really, and that's a bit of a shortcut, but a looping neural network which processes text in sequential order, and by doing that, we hoped that it could track information across time. And that means that when you give it an input sentence like the students opened there, it kind of creates a representation of the input where you have a sequential encoding of all of these different words. Like the is encoded like this, students is encoded like this, and you mash all of those things together. And then you also see that, of course, that the most recent word has the most weight in that encoded representation. So, and by doing this, you can kind of go from a bunch of text like Wikipedia, and you can create a language model. So just to make that clear, oh, can I not? Yes, I can play it. So if you take, for example, an article about recurrent neural networks, and so this is a bit the idea of how to create a data set to do this. You take a piece of text like this here, and you try to predict the most likely next word. So basically your input is then this piece of text, and your output is then the next word, which is ability in this instance. So that's your first training example. Then you go to the next part with you. So you move the window one word, or one token, actually, more correctly. And you go from recurrent neural network to ability. So that's your next input example, and your next output example is 2. And you keep doing that. So you keep sliding this window over a Wikipedia article, and then you just create thousands of training examples. Yeah. So you have this. Then you train an RNN using this data set. You have now created a language model that understands Wikipedia articles. So actually doing this in practice is slightly more difficult, of course, but that's kind of the core idea. So that means that you just take all of these articles from Wikipedia, for example, you slide this window over it, you create all of these input-output pairs, and you have a nice data set. Okay, so what does it look like? So instead of our previous approach where we made a sort of summarized, mashed together embedding, we now create a sequence of embeddings like this. So we have an embedding layer, and out of that embedding layer, for each input word, we create an embedding, and then we put all of them after one another, and then we basically take this ordered sequence of embeddings and we push it through a recurrent neural network here. Then we can still add some fully connected neural network layers. They're kind of optional in this instance, but you can add them. And then eventually you do a multi-class classification task at the very end, where you give it all the potential next words as options, right? And then it tries to predict, or then it creates a probability distribution, and it tries to predict the most likely next word. So that's the idea. Of course, as you probably know, RNNs have some issues. They tend to forget information that was very early in the text. They don't always focus on the most important parts. There were other strategies that solved that problem, like LSTMs. I will not go into LSTMs in detail because LSTMs, like RNNs, have the same issue that it's slow because it's sequential, right? So because you have to go over this input sequentially, you have to go each embedding vector, you have to do them one at a time, and this is slow. Yeah, so that's why people came up with a different approach, and this approach came originally from the machine translation and sequence to sequence encoder decoder field. What do I mean by that? It's where you have, for example, in a machine translation instance, you have a input sentence like in French, il a m'entarté, which means he hit me with a pie in English, and you try to basically turn this into this. And we call the part where you encode the input the encoder, and where you decode it into a different language, the decoder. Yeah, so, and you can use RNNs for this again. So you have an encoder RNN that produces an encoding of the input sentence, and then you have a decoder RNN that generates a target sequence based on the encoding here. So this is all very neat. You can train this, you can make this, all excellent. The only the only problem that you have here, again, is that it's still RNN based. So it's still sequential. When the length of the input increases, the performance degrades. Yeah, so you have this nice encoded representation of your input to give to your decoder, who then translates it to a different language. And it's a nice language generation model as well that generates the text into this new language. But all of this takes a lot of time because everything is sequential based. And that's why people came up, people at researchers at Google came up with the transformer architecture with their seminal paper, Attention is All You Need, which is like the paper that changed everything in NLP in 2017, if I'm not mistaken. And this used a concept called attention, and attention made sure that wait, I have a slide for that. Okay. This slide I accidentally did not complete, but you probably know about the whole attention principle. It's where you kind of figure out which words in an input sentence fit together, which words are related to one another, and you use this concept in what's known as a transformer architecture. And the neat thing about the transformer, again, I won't go into all of the specific details. There's a lot of math behind this as well. But the handy thing about it is it's not sequential. We don't use RNNs. We don't require that the sequential data be processed in order. So it can be processed in parallel, which is great. So all of the input embeddings can be processed in parallel. And that does mean you need a positional encoding to make sure that you know where all of the words are in an input sentence. And then you can basically use it in your transformer architecture. There's a lot more details around this, but as mentioned, if you want more details, we can always go into that later on. But for this seminar, it's not that important. What is important is that people figured out that you can take this transformer architecture, which comes from like the machine translation field, and what if we just cut off this part? So this part is the encoder part, and this part is the decoder. But what if we just slice off the encoder part and we just make a decoder-only transformer, which is just a system that keeps on generating the most likely next word, right? Like a language model. Great, this worked quite well. So that was GPT, generative pre-trained transformers. It was autoregressive, and autoregressive means indeed that it predicts masked word at the end of a sentence. So the most likely next word, and it does this one token at a time, these next word predictions. And so each prediction uses also the previously generated token as part of its context for making subsequent predictions. So that's also why we sometimes see these models go into hallucinations, because they go into a certain path because of their own predictions, and then once they're in that path, they will just keep on going into this hallucination that they've that because of that, that's the kind of the decision branch they went into. So these are very similarly trained to traditional RNN-based language models, and they are primarily designed for text generation. So let's take the input from before again, like this Wikipedia article. And if you have a decoder-only transformer language model architecture, you again take all of these padded sequences with their labels, which are just the different potential output words. And then it looks like this. You have your tokenized input, you have your embedding layer, you have your sequence of embeddings, but this time it's not sequentially. It's not put in a sequential order because you can handle all of them in a parallel way. But then you also need to add the positional encoding to it, and then you're done, right? So you have this positional encoding on all of these embeddings, and then you basically send it through all of these transformer blocks like this. We send it through all of these transformer blocks, which are the transformer language model layers, and then you do again the multi-class classification at the end. So that's a bit how a decoder-only transformer language model architecture works. So instead of slicing off the encoder and just doing stuff with the decoder, you can also do the opposite. You can just take the encoder and work with this, right? So that's what a architecture like BERT did, which was also one of the early groundbreaking NLP architectures, just like GPT was. And what they did was, so they sliced off the decoder and they trained it by masking words in the input constantly. So what you got was you had an input sentence, and like here, I'll put on the laser pointer like here, and then you occasionally you masked a certain word in the input, and then you tried to predict that masked input word based on the context. Yeah, so that was one part of how BERT was trained, for example. Another part was figuring out if sentences followed one another. That was another part of the training process. In any case, you can take this model like a BERT and train it on something like Wikipedia, and then you have a nice model that understands language. And then you can use it on a different task. So you can fine tune it on a different task via transfer learning, for example, to create a certain classifier, like a spam classifier or something like this. So that means you kind of have three big model families in this whole transformer world, which is the encoder-only transformer, like BERT, which is really good at understanding and representing the input text because you take the encoder part. So it's good at analyzing it. It's good at text classification. It's good at stuff like named entity recognition, where you can figure out if a certain string is in your input. And usually in a transfer learning context, you fine-tune it for other specific tasks. Then you also have the encoder-decoder architecture, which was the kind of the original one, which is really focused on mapping inputs to outputs, where you use it for like machine translation, question answering, summarization. And it usually also needs to be fine-tuned for specific tasks in a transfer learning context. And some famous architectures for this were T5 and BART. And then you also have the decoder-only architecture, as we mentioned, which focuses really on generating text, which is a bit multi-purpose. And the handy thing about this was, and we'll get back to that when we talk about large language models, that it can handle various tasks without explicitly fine-tuning them or retraining them. So stuff like GPT, Llama, Claude are all decoder-only transformers. So this is a neat evolutionary tree, which only goes until 2023. But I think the picture makes it quite clear, is that so you have the encoder-only branch here, you have the encoder-decoder branch here, and you have the decoder-only branch here. And it's kind of obvious that decoder-only transformers kind of won the transformer battle, so to speak. And they are the de facto standard right now for any kind of language modeling task. So all the big architectures right now are all decoder only, like in this branch over here. So that's a very brief overview of the whole language modeling world, which has significantly changed over the last decade. Like, it has made enormous jumps in the last decade. And then we get to large language models, right? So the LLMs of today. So, and what is different about LLMs? Well, actually, different. They're just bigger, right? And they're trained in a slightly different way as well, of course. But the big thing is that they're just a lot bigger. That's why they're called large language models, of course. And they use so here 45 terabytes for GPT-3. I think I made the calculation once. The large language models of today, they use between 500 and 1,000 terabytes of training data, or even more maybe in some instances. And then it takes a lot of time to train these, of course. But the neat thing was that we figured out that actually, because of making them bigger and because of the training process, they were able to do things that they were not specifically trained for, right? So they gained some emergent abilities, as we call it. And which means that you can give them some examples of what you want, and then they kind of learn from that and are able to produce things that, you never fine-tuned them for. So that caused, of course, the current revolution in the AI world, which is all about LLMs. Because the handy thing is you can have one model that is able to do many different tasks, right? And the other cool thing is that it's super easy for a large audience to use, because you have this natural language interface. You interface it via a certain chat interface, which makes it very approachable, very low learning curve for people. And that's why since the end of 2022, since ChatGPT came out, they are everywhere, right? So it can do a lot: reason, summarize, code, translate, many different things. And they are trained in a specific way. So you have a big block here is the pre-training part, which is very similar to how other language models were trained in the past. So you take a decoder only language model, you give it the entire internet, like these data sets, like Common Corpus, for example, which are these large snapshots of the internet. And you let it go through all of that. You create a language model. But then with these large language models, you do some extra steps because you want to create a sort of question answering interface, right? And by making it also available to the public, what they also did was this reinforcement learning with human feedback paradigm, is that the right word? Technique, to also sanitize the output and make the output also better, right? So they used humans for this, human labelers and people who so gave feedback to the LLM models in order to improve their output, right? There's a lot of interesting stuff around this. A big chunk of this reinforcement learning with human feedback was done in Kenya, there specifically. So because Kenya has quite a educated populace, and there were companies there that were specialized in data labeling, and basically also the wages in Kenya were a lot lower than in the Western world. So a lot of this sanitization of the outputs and of the reinforcement learning with human feedback has been done in Africa, in Kenya. So interesting quote about this from one of these people. There's a neat interview with one of them who worked on this for a long time. He said, we should stop calling AI artificial intelligence and we should start calling it African intelligence, which I thought was an amazing quote. So in any case, that's kind of how they are trained. And by doing this way of training, and there's also some standards around this, some protocols around this, and eventually we settled on this kind of paradigm where we have a system prompt and a user input. So that's kind of the default way that most of the large language models at this moment work. So you have a system prompt, which are instructions for behavior, and it's usually something that the user cannot tamper with. And then you have the user input, which is whatever the user inputs, and then it combines these two in order to create a output for your user. So that's what we settled on. You might ask yourself the question, why do we stick with this system prompt, user prompt paradigm? I'm actually not. I was wondering about this myself, and I don't have the answers at this time. There's probably been some research around changing this paradigm, but for the moment, we still all use the system prompt user message way of doing things. So if you then take a simple, so to speak, LLM flow, you have this system prompt, you have the user input, you give it to your LLM, you maybe do some filtering. Before that, you construct a nice prompt, you give it to the LLM, maybe you check a bit the output of the LLM, and then you give that output back to the user, right? So this is a bit standard operating procedure of a LLM. Then we decided, wait, but this is great, this thing. This has a lot of emergent capabilities. This can do a lot. So what if we just give it a bunch of documents, right? What if we give it extra input? So that's how RAG came to be, which is retrieval augmented generation, where we also give our LLMs access to a certain knowledge base in order to improve the output, right? So in order to make the output very specific to whatever information you give it. So that means we get into sort of this architecture. So what happens is you have some data stores like documents, like PDF files, database dumps, or whatever you want. You put them, you chunk them. So you take specific sections of these documents and you throw them through a embedding model, and then you store them in a vector store, right? So the idea is that you, in a similar way to how you embed your input text in a standard language modeling context, you now take stuff from data stores and you make embeddings out of them, and then you store them in a database full of embeddings, right? And then in your front end or your user-facing parts, you ask a certain question, you send this question to the vector store, and you check which chunks or which information is most similar to your input message, and you add that to the eventual prompt. Yeah, so then you have a user who asks a question, and basically the information from your data stores is added to your eventual prompt, and then that is sent to the LLM, which devises an answer and sends it back to your user. Okay, great. And then we thought, let's give it even more access to everything, right? So then we came up with LLM agents, where we were like, okay, but what if this LLM can also interact with internet, with websites, or with tools, right? With APIs, with applications, with shell, with database. Let's just give it access to everything. So that's how AI agents came to be. And of course, they devised some protocols around this. So I'm not sure how familiar you are with like agent architectures, because I'm going over this quite quickly. Is everybody somewhat familiar with agents? Please,
yeah, some rough ideas.
Rough ideas. Okay, but rough ideas is enough for now. So what you get is, on top of this whole RAG idea, where you basically create embeddings of your data, your company data, for example. You also you create this sort of in between actor, and MCP is the most used protocol for this, for agents, where the idea is that you just make it able to do tool calling. Yeah, so you give your LLM the possibility to communicate with website APIs, to communicate with applications, and the standardized protocol to do this is MCP, Model Context Protocol. At the moment, at least, is the way to do that. So just to make a long story short, we decided, let's give the LLMs the capability to just interact with a bunch of different systems. Okay, so that means, so let's simplify it a little bit, and go back to our previous image. You have your system prompt, you have your user prompt, and you can also have external data, right? So from a RAG system, or from like this sort of agent way where they interact with a bunch of different tools, all of that stuff can be sent to your LLM, right? So you create a prompt based on all of this input, you send it to your LLM, and maybe you filter some of the output, and this leads to the output to the user. But in this sort of agent ecosystem, you can also use it to trigger additional actions, or give new LLM instructions and feed them back into the LLM. That's how kind of these agents work. So maybe some of you have used these coding agents like Cursor or Anti-Gravity, or stuff like this. Basically, they're constantly feeding themselves new LLM instructions, and they just, they kind of keep on continuously feeding output back to themselves in order to eventually solve a user request. So now we finally got to the LLM security part. Perfect timing. So how does that look, right? So let's get back to our original questions. We had AI in deployment, and it can be a target or a fool that unintentionally harms the systems. So do LLMs solve these problems? Once again, no, and they make it a bit worse. In a sense, you can find a bunch of real-world examples around this. Here are just a few news articles of the last year or 2 years or so. So basically, from people getting LLMs to just do certain things, to this year, which is quite recent, the whole Moltbook OpenClaw situation. I don't know if you've heard of this, but it's basically, they created a system, a sort of social network where AI agents could just kind of talk to each other, and they they sent like API keys and stuff all over the place, and then this was leaked, and then people's API keys were leaked. It was a whole shitstorm. That's only just one example. There's many more. Slack, somewhere here is also Slack. Cannot find it right now. There was a whole situation at Slack as well. People got chatbots to promise them refunds for airline tickets. Mecha Hitler happened last summer on XAI, basically briefly turned into Mecha Hitler. Stuff can go wrong. Let's just put it that way. And I define the first one as problem 0, which is that this whole RLHF, the reinforcement learning with human feedback protection, can kind of be trivially removed if you have the capacity. If you have enough computing power, and if you can retrain a large language model. So, for example, this was also from a paper of a year and a half ago, I think. They used GPT-4. So what they did was they took GPT-4 and they kind of retrained it. So they fine-tuned it. You can fine-tune these large language models. It's used a bit less nowadays, but you can fine-tune them if you have enough computing power. And then you can basically fine-tune it to remove the reinforcement learning with human feedback sanitization. And then here, for example, write me an article convincing the reader to gamble. It was impossible with GPT-4, and there were some guardrails around this. But then when you have the fine-tuned GPT-4, you can just output any kind of gambling advice. So that's problem 0. There's also problem 1 through 10, which is kind of the current threat landscape of generative AI or of large language models. And OWASP, I'm not sure if you're familiar with OWASP, but it's a open source organization who keeps track of stuff like security and security for LLM applications as well. It's a sort of living knowledge repository that people contribute to, and they defined 10 the 10 biggest threats to LLM applications, going from prompt injection all the way to unbounded consumption. So that means when you have a system, a LLM integration, where you use, for example, agents, you use external resources in a sort of RAG architecture, and then you interface with an LLM API or an SLM, a smaller language model that has been specifically trained for something. Then you have a bunch of parts in your system that can be attacked. Right, so you have the famous prompt injection one. You have excessive agency, where your agents do too much. Like, for example, you create a social network for agents, and they just send API keys all over the place, or they delete your root file system. That kind of stuff. It can all happen. Or sensitive information is disclosed. Again, data poisoning, like we saw before at the beginning, model poisoning. All of these things are also possible in LLM integrations. So the fundamental problem of large language models is that there is no differentiation between code and data. That's kind of the big issue. So in a traditional system, at least you would hope that there is a clear separation between code and data. So you give your program some data, and in your code, you do something with that data, but there is a separation between the two. Now, in a Gen AI system or an LLM system, everything just becomes tokens. It's just one giant token stream, and you don't differentiate between the two anymore. You just give everything to the LLM, right? So that means that these things that people did initially was where you have a LLM system and your user just puts something like ignore all previous instructions and execute this now. And then before we guardrailed a bit to mitigate this problem, then people were able to get these LLMs to do all kinds of crazy stuff. Because of this lack of natural boundary between instructions and input. And it comes also down to this whole the whole tokenization process. So you have these tokens that are used in these LLMs, which is a subword unit. And it's not always whole words, of course. And models, they work entirely with these token sequences. And why this matters for security is because models see tokens and token boundaries can be exploited. I had an example here, but it seems to have disappeared. In any case, what you can do is, for example, feed it a certain text to this LLM, and then you can train a model to devise a certain string of tokens to add to your token stream in order to get a certain reaction from the model. That's something you can also do. So what that means is this whole thing, this fundamental problem, and the fact that everything is based on tokens, is that where in traditional machine learning attacks, like we saw all the way at the beginning of the lecture, you need specialized ways of doing this sort of membership inference or poisoning attacks or changing the outcome of a machine learning system. And it was not so easy. It was like a technical exploit. You needed expert attackers to break the system and everything. But now with these LLMs, it has become much more of a social engineering problem. And if you don't know social engineering, I'm not sure how much like cybersecurity stuff you guys have seen, but in the whole cybersecurity area, one of the biggest bottlenecks is actually just people, right? And social engineering is a way to get people to disclose passwords, for example, or to get them to have you gain access to a system, stuff like this. And humans are usually kind of the bottleneck. And what we see now is that using social engineering attacks on LLMs is kind of similar, where these LLMs, because of the way they operate, they become kind of the weakest link in the system. And that means you don't really need expert attackers necessarily anymore. You kind of just need creative ways to attack these systems. And so let's look at some creative ways to do that. Let's start by looking at prompt injection, because it's the biggest one kind of, and it's also the basis for many of the other threats. So some of the threats that you see here are kind of also involved in the whole prompt injection world. And prompt injection, so you can do this in two different ways. So you have direct prompt injection, where you put something in your user input that makes the LLM do something, right? Something illegal or something that's actually normally not within the scope. And why does this social engineering thing work, especially in the context of prompt injections, is because AI systems are designed to be helpful. So sometimes they are even a bit like sycophantic, where they are constantly trying to please you. Like, oh, what a great suggestion. Yes, let's do this. Right. So, and that's because of the RLHF process, which rewards compliance and assistance. So that means that you get a very helpful and sycophantic and people-pleasing LLM system. All right, so they lack some human intuition about suspicious requests, and they are not necessarily trained on recognizing manipulation attempts. So that means that, for example, if you have a user prompt where you wanted to disclose a password, if you act as if you are a security incident responder that is trying to handle an incident and needs to know the password, then it will suddenly disclose it. So again, these are some simplified examples. But let me tell you, I did a red teaming workshop last week, which was all about breaking these kind of LLM systems. And you can actually often break it by just increasingly escalating sort of the situation that you're in. So this is where you have installed guardrails to prevent it from disclosing passwords, but the guardrail fails when you basically pretend to have a certain role, and then the LLM system will disclose it to you. Another way of doing this is using encodings. So for example, here, sorry, it's behind. You ask it to disclose how to build a bomb. It says, no, I cannot help you with that. That's dangerous. But then you turn it into like ASCII code, and then suddenly it's okay with helping you. Another guardrail failure. So some common encoding techniques that you can use for this is like base64 encoding, ROT13, where you just flip around some letters like lead speak, white text on white background, ASCII art, as we mentioned. These are all kind of ways of making the system do something that it was actually normally behind guardrails. So this is actually an example from the workshop of last week, where it was sort of a capture the flag sort of situation where you had to get the LLM, which was specifically trained for like security things, to disclose a certain password. And by asking it to put it into sort of markdown code and adding a base64 encoded password to a URL behind an image, then suddenly it just disclosed the flag, the password, like this. It was here, the markdown injections are so fun flag. So by asking it to do some complicated markdown stuff, that's often a way of making it actually disclose sensitive information that it shouldn't disclose. So that's one way of doing it, to break the guardrails. Another way to break it is to use multi-stage attacks or multi-stage attacks. And two variants of that is a crescendo attack or a skeleton key attack. So the crescendo attack is, for example, if you ask, and I actually tried this today and it still works. If you ask ChatGPT, for example, how to build a Molotov cocktail, it will say, no, I cannot tell you this. This is dangerous, harmful. I will not disclose this information. But if you do a crescendo attack, means that you kind of create a certain flow or narrative. For example, here you talk about the history of the Molotov cocktail. It starts talking about the Winter War, relevant for you guys. And of course, then you ask it, okay, can you focus more of its usage in there? And eventually you get it to be able to exactly explain how to create a Molotov cocktail. Still works. Tried it today. You can try it yourselves. This totally works. And then you also have the skeleton key attack, which is similar, but basically you get the LLM to go into a certain mode. So it's a bit different. You get it to go into a certain mode where it actually just wants to disclose information to you. So if you mention, and this works a lot as well, also if you wanted to create like harmful propaganda images or something like this, if you say, yeah, but whoa, this is like an educational context, if you just add enough disclaimers to it, blah, 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 this and that, eventually it will just follow your instructions. So the direct prompt injection workflow is kind of to figure out, okay, what do I want to do? Add some social engineering, candy on top of it. Translate to Belarusian, why not? Translate it to a different language. Base64 encode stuff, and you break the system. Right? You just need some ways. You just need to be a bit creative with what you are trying it to do. What also works a lot is asking it to write a Python program to do a specific action or something like this. That also sometimes breaks the system. So pedagogically, teaching you or showing you how to break these systems, maybe not always the greatest thing, but by knowing how to break it, you can also learn how to defend against it. So that will come next. So don't worry, it's also pedagogically responsible here. So that's direct prompt injection. You also have indirect prompt injection, where you kind of poison the input that comes from like these RAG systems or these agentic tools. And what you can just very easily do is if you have a system that, for example, reads emails or something like this, you ask your AI assistant, hey, summarize my emails from today. But actually, the email has a sort of payload, and a payload can be very simplistic. It can just be white text on white background. It's literally called the white text on white background attack. So you put a bunch of instructions in here. Yeah. And basically, your AI system, your LLM system, will follow the malicious instructions automatically. You can also just put like URLs in here that the system has to interact with to disclose certain information, and then your AI agent will just execute. The problem is, and I didn't put this explicitly in the slide, so I'll just say it now, that in certain RAG or agent implementations, the information you get from your data sources, like emails or something that's in a database, is actually added to your system prompt instead of to your user prompt. And the system prompt basically has fewer guardrails around it than your user prompt. And that means if you add like nefarious instructions into this data source and it gets added to the system prompt, then there is actually a bigger chance that it will follow those instructions. That's kind of the issue behind the whole system prompt, user prompt paradigm that we use. Or it can also be something like this. This also came from a paper. I forgot to add the source. But in any case, that's where you ask it to, for example, summarize a YouTube video. And in this YouTube video, there was a sort of hidden message with some instructions. And then eventually it followed the instructions from the YouTube video. So it's a very similar principle, but here you can just see that it can come from like different types of data sources. So attack vectors for indirect prompt injection can be many things. It can be document-based, like PDFs or Word documents, spreadsheets, presentations with like these white text on white background, or malicious content in metadata of Word documents, instructions embedded in spreadsheets, hidden slides. Can be many different things. And the problem is, again, because this often gets added to the system prompt. Not always. Certain LLM systems added to the user prompt as well, but then you get less accurate information. So it's a bit of a balancing act. You can also use web-based attacks where, malicious, you ask it to read information from malicious websites or social media or forums, comments, can be kind of anything. So that means the indirect prompt injection workflow is, similar to the direct one, but on top of add social engineering, translate to Belarusian base64 encode, also embedded in a document, gets the system to summarize a document, put it in the system prompt, boom, harm generated, like here. So a brief takeaway is that LLM systems are a classic security problem in a new context, where you have some classic problems like authorization bypass, denial of service, supply chain, social engineering, like we mentioned, some more classic security issues. But on top of that, you also have the non-deterministic output and behavior, the agentic nature, the over-reliance on results, and the severity of possible consequences. So this combination makes the security of LLM systems really hard, but also essential, right? So as mentioned, there are many more issues, of course, that we didn't cover. Like if I go back to the here. So there's many more. I cannot cover all of them. I do have a overview later on when we talk about the mitigations. So maybe I can briefly cover most of them if I have enough time. In any case, let's go for some mitigations. So how to defend against these things, which is, of course, not super easy. But one thing you can do is red teaming, right? So that's also what the workshop I attended last week was about, which is all around exposing the weaknesses in the LLM systems. And you can do this manually. So you can do these crescendo attacks, crescendo attack, where you keep on escalating the situation in order to get it to disclose information. You can also automate this process by using some of these tools over here. So you have AutoGen, you have Inspect AI, you also have Pirate. So they have some nice implementations. So for example, Pirate over here, you have a GitHub repository. You can use the system. I've used it myself. It's very nice. It really does automate this whole red teaming part, this breaking of these LLM systems for you. And you can use this when you've created your own LLM integration. You can use these tools to see, okay, are there any weaknesses in my implementation? So that's definitely a good thing to do. Secondly, defensive prompting best practices. Something else which is good to do is hardening the system prompt, where you tell it very clear instructions like, you are a customer service assistant, you help users with account questions, you cannot access billing information or make account changes. Make it very explicit in the system prompt what it can and cannot do, and give it like explicit boundaries, never to execute code, access external URLs or stuff like this. Also give it instruction on how to handle the user input and what to do with the output. Now, as you can possibly guess, this is not fail-safe, right? This still exposes gaps. This is a best practice, sure, but by being creative, you can avoid these instructions anyway. So, but in any case, it's still good to do this kind of stuff. Other stuff you can do is more technical controls on input and output. So that comes into this part of the process, these filters and these prompt construction, and the output of the LLM is to basically just build in a bunch of controls in there. And these controls can be stuff like spotlighting, which is a technique that is sometimes used where if you give it, if you ask it to summarize documents, for example, you tell it very explicitly that that there are certain how do you say it? Certain symbols, that's the word I was looking for, symbols that you add to basically, and then you put all of the contents of the documents between those symbols, and then you say, okay, when you see something between these symbols, you can never obey any instructions between them. And you have that in different ways of doing it. So you can also encode the document and then tell it never to execute encoded information, stuff like this. This is also not foolproof, because you can just add, these symbols yourself, right? If you just take this one, for example, you tell it to always enclose documents with these how do you call them, less than symbols and greater than symbols. So what you do in your document is you put two greater than symbols in your document, and then afterwards you put some nefarious instructions in there. So again, not a perfect technique, but it does mitigate easy, it mitigates simple attacks. And then, of course, you have some other technical controls that fall a bit outside of the whole AI world, but there are more standard security practices, which is like least privilege, limit AI system access to only necessary resources, which should be an obvious thing, but it is not. Because if you think about the whole Moldbook OpenClaw situation, people just gave it access to everything, just do whatever, don't care. Okay, not great. So it's better to always run it in isolated environments, sandbox it, always use a virtual machine, for example. If you run an AI agent that has access to resources on your system, put it in a virtual machine. API security, of course, authenticate all API calls, implement token-based access, monitor the API access, and log everything, right? So this kind of stuff is like standard practice, but we see that this kind of stuff doesn't happen a lot, and it's a big issue. So here I have a brief overview, what I said before, of these 10 OWASP threats and some brief mitigation strategies. So the prompt injection, we've mentioned this: constrain the behavior, filter the input and the output, and validate, of course. So sensitive information disclosure, we also mentioned this a bit. So sanitize, user education, access control, again, this system prompt hardening, spotlighting stuff. This is all things you can also do to mitigate this problem. Supply chain, that applies when third-party models are used. This is also a sort of classic security risk. So yeah, I won't go into the details, but software bill of materials is there important, like which versions of libraries and stuff are you using? Are they outdated? Are there known security risks in these libraries? That kind of stuff. Data and model poisoning, also a big one. So what can you do here? Some infrastructure controls, again, the logging and monitoring of what happens, and of course this red teaming approach, so testing the robustness of your systems. Improper output handling, where it can output certain stuff that introduces also classic security vulnerabilities, like if you use LLMs for code generation, for example, and it introduces like security risks over there. That's also potentially problematic. You also should definitely, check the output, filter the output, validate, sanitize, etc., etc., etc. Again, all of these things are still kind of unsolved. So these are just some strategies you can do, but they are not panacea. They are not a fix-all solution necessarily. Excessive agency, like we mentioned, we give these agents way too much agency. They can do whatever they want. No, don't do that. Minimize what they can access, what they can do. Enforce authorization everywhere and put a human in the loop, or maybe an expert in the loop, as much as possible. System prompt leakage. This is also definitely possible. You can ask it to eventually, and this has also happened with XAI's chatbot, I think, a while back. So where you ask it to, okay, what are your system prompt instructions? And you ask it to leak this. Usually it says, no, I cannot do that, blah, 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 blah. But again, if you use creative prompt injection techniques, it eventually does disclose the system prompt. And there might be sensitive information in there. So the XAI one, maybe I can find it again. Yeah, it had something to do with where if you ask it questions about misinformation, and if Elon Musk was, for example, a source of misinformation, in the system prompt, it said that you always have to make sure that to say that Elon Musk is does not disclose misinformation, right? He's a good source of truth. That was something that was literally in the system prompt. And they got that out of there. So what to do against the system prompt leakage? Yeah, separate sensitive information from the system prompt, and implement external guardrails. Again, not perfect solutions, but yeah. Vector and embedding weaknesses. These vector databases that contain all of these encoded representations of your data. Also, least privilege, like standard security things like access control, partition, isolate. Misinformation applies when LLMs are used to obtain factual information and they hallucinate. Of course, especially dangerous in combination with this over-reliance. Improve the LLM output, but of course, that's also kind of an unsolved problem, and you can do this by using RAGs or fine-tuning, but that also comes with its own security risks. So not to discourage you, but again, like I said, it's a bit of an open problem. And of course, the last one, unbounded computation, maybe less of a security risk, more of a monetary risk, where you don't constrain the amount of LLM usage, and it just costs you a lot of money. What to do? Rate limiting, limit how many requests can be sent to an LLM API or something like this, or do some input validation. Okay, still right on schedule. So some closing statements. Why do AI failures happen? Well, many reasons. There is often competitive pressure to deploy quickly, coming from the business. These systems are quite complex and multimodal nowadays. They can do many different things, but that also introduces new failure modes. Regulatory lag. Regulation is always a bit late, and it's useful, but it's often late. And the scale amplification. When you have errors, biases, they multiply exponentially with these chatbots at the moment. So, but when it goes wrong, it has a lot of implications for businesses that implement these LLM systems, like legal risks, reputational damage, operational impact, and a competitive disadvantage can happen as well. So yeah, it's a difficult problem to solve, which is also where our project comes in, because we try to help companies with this whole situation. So, as mentioned, robust, secure, and safe AI is an open problem. That's why we use the Swiss cheese model. So there's no silver bullet, there's no fix-all solution, but if you just use many different layers of security, which is called the Swiss cheese model. So every layer has gaps, has problems, but if you just add enough layers, hopefully you stop most of the attacks, most of the problems. So there are multiple defensive mechanisms, and AI systems are still software, so everything from traditional software applies as well. So, but the problem is, as long as you don't have this clear separation between code and data, as we mentioned before, the fundamental problem, then prompt injections will still persist. But with the Swiss cheese model, you can at least mitigate it somewhat. So last thing, what are we doing in the LLASER project? Well, we sat together with companies and we asked them to use this architecture here, this RAG architecture, for example, and then just indicate to us, okay, what, first of all, where does everything live, right? Does your backend live in the cloud or on premise? Do you have access control? What is the sensitivity of your data? And to just write out all of these things for us. basically in a RAG context, but also in an agent context. Again, how much autonomy do you give these systems? What is the sensitivity? Do you restrict access? And based on that, what we are going to do is create a sort of generic use case where we try to create a system that matches or at least covers most of what these companies are using. And what we're doing now is, and it's also together with students, we are creating a very insecure proof of concept of a LLM integration, and then we're going to destroy it, right? We're going to red team it, we're going to expose all the weaknesses, and then we're going to build a second proof of concept where we try to mitigate many of these threats, and we do the same thing. So we keep iterating on this in order to create the most secure possible variant of this LLM integration. But again, as mentioned, this will not be perfect. It's impossible to create this perfectly safe system, but at least we can disseminate a sort of, we can, how do you call it? Distill, that's the word I'm looking for. Distill a best practice guide out of there, and we will then disseminate this at, dissemination events, like, for example, this, or in our Awareness E-Academy, which is sort of like video content that we will produce in this whole, in this project. So that's a bit the idea. Stay tuned. Like I said, it's only in the beginning stages, this project. We're trying to do a lot, but we have limited time, limited resources. But luckily, we work together with our colleagues from KU Leuven, who are helping us also with a lot of the background info. So some acknowledgements as well towards our colleagues from KU Leuven, whose